Welcome back, everyone. Poland is advancing in the field of compact particle accelerators, with research aimed at applications in industry, healthcare, and physics. These developments are being supported by government programs, universities, and collaborations with European laboratories. The technology builds on decades of accelerator science, but now focuses on smaller, more efficient machines that can be placed in hospitals, factories, and research centers. This video will explain how particle accelerators work, how Poland is contributing, and what the near future may bring. Subscribe now. To begin, a particle accelerator is a device that increases the speed of charged particles using electric fields. The most common particles used are electrons or protons, though some accelerators use heavier ions. The particles are guided and focused by magnetic fields while gaining energy from oscillating electric fields. Traditional large machines like the Large Hadron Collider at CERN rely on kilometer-long circular tunnels to reach very high energies, but compact accelerators aim for smaller scales. The basic principle remains the same, but the engineering differs to make them practical for non-physics applications. Poland has several institutions working on accelerator development. The National Center for Nuclear Research, known as NCBJ, plays a central role. Located in Swerk, it operates research reactors and accelerator facilities. The Polish Academy of Sciences also supports related projects through its Institute of Nuclear Physics in Krakow. These institutions collaborate with European organizations such as CERN and DESY in Germany, but they are also developing technologies tailored for industrial and medical needs. Government programs, partly funded by the European Commission, provide grants that encourage domestic innovation in this field. Compact accelerators typically use linear designs rather than circular ones. In a linear accelerator, or linac, particles are accelerated in a straight line through a sequence of cavities powered by radiofrequency sources. Each cavity imparts a small boost, and the boosts add up as the particle passes through. Poland is focusing on superconducting linac technology, which reduces power consumption and allows continuous operation. The use of superconducting materials like niobium at cryogenic temperatures lowers electrical resistance, which increases efficiency compared to older copper cavities. This principle is also being advanced at facilities such as Fermilab in the United States and at DESY. One of the most immediate applications of compact accelerators is in medicine. High-energy particle beams can be used for cancer treatment through a method known as proton therapy. Instead of X-rays, which pass through tissue and affect healthy cells, proton beams can be tuned to deposit most of their energy at a specific depth. This reduces collateral damage. Poland opened its first proton therapy center in Krakow in 2011, using a larger cyclotron, but researchers are now pursuing smaller accelerators that could be installed in regional hospitals. Companies such as Varian Medical Systems and IBA in Belgium are market leaders in this technology, and Polish groups are working with them to adapt designs. Accelerators also have applications in materials testing and industrial inspection. High-energy electron beams can be directed onto targets to produce intense X-rays. These X-rays are used to image turbine blades, welds, and semiconductor wafers. Unlike traditional X-ray machines, which rely on tubes, accelerator-driven X-ray sources provide higher energies and brightness. This allows imaging of dense or thick objects with higher precision. The Institute of Nuclear Physics in Krakow has tested linear accelerators for non-destructive testing, similar to systems used at Airbus facilities in Germany. In 2026, Polish companies plan to integrate such accelerators into aerospace component inspection lines. Another promising field is isotope production for medicine. Many diagnostic scans, including PET imaging, require short-lived isotopes such as fluorine-18. Traditionally, these isotopes are made in research reactors or large cyclotrons. Compact accelerators can produce them locally, reducing supply chain problems. Poland currently imports much of its medical isotope supply, but researchers at NCBJ are developing small accelerators that can generate isotopes on demand. This would benefit hospitals across Central Europe and lessen reliance on foreign reactors. Reports in journals like IE Spectrum note that compact accelerators are becoming a preferred alternative to nuclear reactors for isotope supply. To understand why compact accelerators are so challenging, it's important to look at the underlying physics. As charged particles accelerate, they emit radiation whenever they're forced to change direction. In circular accelerators, electrons lose energy through something called synchrotron radiation, and this loss grows as the energy increases. Linear accelerators can avoid this particular loss, but they require long structures to reach high energies. That's why engineers are experimenting with advanced acceleration methods. One approach currently under study at Polish institutions is plasma wakefield acceleration. In this method, a laser or a particle beam excites a plasma, creating super strong electric fields that can accelerate particles over very short distances. This method is still experimental, but it shows a lot of promise for the long term. Poland isn't working alone in the pursuit of compact accelerators, but its programs are definitely gaining recognition in Europe. In 2024, the European Commission funded the Eupraxia project, which involves several countries, including Poland. The goal of this project is to demonstrate plasma-based accelerators that could fit within a building instead of needing kilometers of tunnels. The Institute of Nuclear Physics is one of the partners in these studies. While the first prototypes are still being tested, this collaboration gives Poland some valuable direct experience in next-generation accelerator design. If everything goes well, this technology could eventually be transferred to Polish industry, especially for medical and inspection uses. It's useful to compare these new developments with older accelerator types like betatrons. Betatrons, which were invented back in the 1940s, accelerated electrons in circular paths using changing magnetic fields. They were widely used for producing X-rays in industrial radiography, but they had some limitations in terms of energy and efficiency. Compact linear accelerators, on the other hand, surpass betatrons by delivering more precise and powerful beams, and they're much more adaptable. These days, betatrons are mostly obsolete, and linacs are replacing them in many inspection tasks. Looking at this historical perspective, you can see how Poland's research aligns with trends toward more efficient and versatile machines. Beyond medicine and industry, compact accelerators are being tested for environmental applications. High-energy electron beams can treat flue gases from power plants by breaking down nitrogen oxides and sulfur compounds. The technology was pioneered in Japan and tested in Poland at the Pomorzany Power Station in Szczecin. Research published in Science Advances shows that electron beam treatment can cut emissions at lower cost than some chemical scrubbers. The method can also be applied to waste treatment and sterilization. Polish researchers are now exploring portable units for municipal waste facilities. It is worth noting the role of Polish companies alongside academic labs. Solaris Synchrotron in Krakow, though primarily a research facility, partners with firms to develop commercial technologies. Electronica, a Warsaw-based company, has produced linear accelerators for industrial X-ray machines. These companies demonstrate how expertise developed for physics research can transition into products. Varian's accelerator equipment is already deployed in Poland's cancer treatment centers, and future procurement could include domestic contributions. The funding model for accelerator research in Poland involves both national and European sources. The Ministry of Science and Higher Education funds domestic programs, while the European Commission's Horizon Europe framework supports cross-border projects. Grants often require participation in larger consortia, so Polish labs join with groups from Italy, Germany, and France. This integration ensures access to advanced facilities like DESY's free electron lasers, where Polish researchers test components before bringing them home. The combination of local expertise and European cooperation really accelerates progress while spreading costs. The medium-term outlook for Poland's accelerator research suggests that by 2026, smaller linacs will be operating in hospitals and inspection sites. Proton therapy centers are set to expand beyond Krakow, thanks to more affordable compact designs. Industrial firms, especially in aviation and metallurgy, will start adopting accelerator-based testing for quality assurance. Research groups are expecting that isotope production units will begin to replace imports, which should offer faster diagnostics for patients. But each of these advances requires engineering reliability, not just breakthroughs in physics. That's why Polish universities are now adding specialized programs to train technicians and engineers in accelerator science. Still, longer-term challenges remain. Compact accelerators have to balance cost, size, and energy output. Hospitals can't afford overly complex cryogenic systems, so researchers are testing simpler designs. Industrial units, on the other hand, must be able to withstand heavy use in factory environments. Plasma-based accelerators, while definitely promising, still face issues with beam stability and reproducibility. Journals like Nature Nanotechnology have published reports showing that even though the acceleration gradients are impressive, maintaining control is really difficult. These limitations mean that conventional superconducting linacs will probably dominate for the next decade, with plasma methods coming into play a bit later. International cooperation is going to shape Poland's accelerator future. CERN is still the global leader in high-energy physics, and Polish scientists continue to contribute to experiments there. But compact accelerators are more about applied science than fundamental discoveries. Because of that, partnerships with companies like IBA and Varian might end up being just as important as collaborations in physics. Polish engineers are learning how to adapt high-end physics tools into reliable medical and industrial machines. This balance of science and engineering is essential for moving from laboratory prototypes to widespread use. Educational institutions also play a role. The Warsaw University of Technology and AGH University of Science and Technology in Krakow are training the next generation of accelerator specialists. Courses include vacuum technology, cryogenics, radiofrequency engineering, and beam physics. Student groups often visit European labs for internships, building a workforce capable of maintaining advanced equipment. By developing human capital alongside machines, Poland ensures that the accelerators will not only be built, but also supported for decades. This combination of education and infrastructure secures long-term viability. Looking at global comparisons, compact accelerators are also advancing in Japan, South Korea, and China. Japan's Ministry of Communications has backed compact accelerators for semiconductor inspection. South Korea's Carey Institute has demonstrated electron beam units for sterilization. China has begun installing hospital-based proton therapy accelerators in multiple cities. Poland is smaller in scale, but its integration into European networks and its targeted focus on industrial and medical applications allows it to remain competitive. Reports in IEEE Spectrum emphasize that accelerator technology is becoming decentralized, with many nations building specialized units. From a societal perspective, the implications are broad. More affordable cancer treatments reduce patient travel and waiting times. Local isotope production improves healthcare efficiency. Industrial accelerators improve product safety, reducing failures in aircraft or pipelines. Environmental accelerators offer new tools for pollution control. Each of these cases illustrates a direct path from physics research to everyday life. For Poland, the strategy ensures not only scientific prestige but also economic and health benefits. Government support will be necessary to ensure deployment beyond pilot projects, as costs remain significant. Another area of progress is accelerator-driven neutron sources. Neutrons are valuable for probing materials since they interact with atomic nuclei rather than electron clouds, giving information that X-rays cannot provide. Large facilities, such as the European Spallation Source in Sweden, are leading this field. But compact neutron sources are now being designed for universities and regional labs. Polish researchers are evaluating accelerator-driven subcritical assemblies that use high-energy protons to produce neutrons through spallation. These smaller systems could make advanced materials research more accessible and reduce dependence on large multinational labs. Polish accelerator development also benefits from advances in computing and simulation. Modern accelerator design uses particle-in-cell codes and electromagnetic solvers that run on high-performance computing clusters. The Interdisciplinary Center for Mathematical and Computational Modeling in Warsaw provides resources for such simulations. These tools allow engineers to optimize cavity shapes, beam focusing elements, and shielding configurations before any physical components are built. This reduces costs and accelerates development timelines. The integration of computing with accelerator science ensures that Poland can test bold designs virtually before committing to expensive prototypes. In closing, Poland's work on compact particle accelerators shows how advanced physics can translate into practical technologies. From linear accelerators in hospitals to industrial X-ray inspection units and environmental treatment systems, the applications are diverse and impactful. Challenges in cost, complexity, and reliability remain, but steady progress supported by European partnerships suggests that by the late 2020s, many of these accelerators will be operational. The combination of scientific research, government support, and industrial collaboration places Poland in a strong position to contribute globally. Thank you very much for watching. Please like and subscribe.